What if the very thing that made an engine legendary was also the thing that destroyed it? In 1944, German engineers solved a problem that had crippled military vehicles across 2 continents. Their solution worked so well it dominated farms and construction sites for the next 50 years. Production numbers climbed into the millions. And then, almost without warning, it disappeared. The Deutz F6L912 wasn't replaced by something better. It wasn't outcompeted by a rival manufacturer. It was brought down by something hiding inside its own design from the very beginning. To understand what killed this engine, we have to go back to the problem that created it. By the early 1940s, Germany's military was fighting a war on 2 fronts, and their vehicles were losing a different battle entirely. On the Eastern Front, winter temperatures plunged so low that coolant turned to ice inside engine blocks. Hoses split. Water pumps cracked. Radiators burst. Vehicles that had survived enemy fire were being destroyed by their own cooling systems before they could reach the front lines. North Africa presented the opposite nightmare. Desert heat pushed cooling systems past their breaking point. Radiators boiled dry. Engines overheated so frequently that entire columns would halt, waiting for machines to cool down before they could move again. For an army that depended on mobility, this was catastrophic. Military planners posed a radical question to the engineers at Kluckner-Humboldt-Deutz. What if we eliminated water cooling entirely? No radiators to puncture, no hoses to freeze, no coolant to boil away, just metal fins and moving air. The same principle that kept motorcycle engines from melting. By 1944, the first Deutz air-cooled diesels were rolling off production lines in Cologne. The concept had already proven itself in limited combat use. But Deutz wasn't just copying what existed. They were building a foundation for something that would outlast the war by decades. What nobody realized yet was that this foundation contained a flaw, not a manufacturing defect, not a design oversight, something more fundamental. And it would take half a century for that flaw to finally catch up with them. The war ended, but the technology found a second life. Deutz looked at what they had created and saw potential far beyond the battlefield. If these engines could survive combat conditions, they could certainly handle a harvest. If they could run in frozen wastelands and scorching deserts, they could work on farms that lacked spare parts, construction sites miles from the nearest mechanic, industrial operations where downtime meant disaster. Turning that vision into production took longer than anyone wanted. Germany's industrial base lay in ruins. Factories were bombed out. Supply chains had collapsed. Skilled workers had scattered across Europe or hadn't come home at all. Deutz spent the rest of the 1940s just trying to rebuild what the war had destroyed. They didn't return to full manufacturing capacity until the early 50s. But once they did, the numbers told a remarkable story. 100,000 air-cooled diesels shipped by the middle of the decade. Then, the growth accelerated. By the late 1980s, total production had climbed past 4 million units. These engines were working on every continent, in climates ranging from Scandinavian winters to equatorial summers. The 912 series emerged in the late 1960s as the flagship of this expansion. Deutz designed it as a modular family, engines that shared core components across different configurations. Need a compact power plant for a small tractor? The 3-cylinder version delivered. Need serious muscle for heavy equipment? Add cylinders until you reach the 6-cylinder F6L912 at the top of the range. That flagship model displaced just under 5.7 liters across its 6 cylinders. Deutz chose what engineers call an undersquare design, with the piston traveling farther than its diameter on each stroke. This geometry favored pulling power over high-speed operation, exactly what agricultural and construction equipment demanded. Depending on tuning and operating speed, the engine produced anywhere from 65 to 106 horsepower, with a torque curve that stayed fat and useful across a wide range of conditions. But specifications alone didn't explain why operators loved these engines. The real appeal was philosophical. Everything about the F6L912 was designed for the person who would eventually have to fix it. The cooling fins that wrapped every cylinder looked industrial, almost brutal, like armor plating with ridges. A belt-driven fan forced air across the surfaces, carrying heat away without pumps or hoses or thermostats. No coolant to check, no radiator to flush, no freeze plugs to worry about when temperatures dropped. The engine's internal architecture took this thinking even further. Most diesel engines treat the cylinder block as a single integrated casting. Damage one cylinder, and you're dealing with the whole assembly. Deutz took a different approach. Each cylinder mounted individually to the crankcase. If something went wrong with one, a mechanic could unbolt it and pull it free without disturbing anything else. The repair might take hours instead of days. The machine could be back earning money by the end of the shift. This was the promise that sold 4 million engines. Simplicity, reliability, the ability to keep working in places where complicated machinery would strand you. Operators who had spent years nursing temperamental water-cooled equipment felt like they had found something they could finally trust. What they didn't know yet was that simplicity always comes with trade-offs. And this particular trade-off was already generating heat in ways the cooling system was never quite designed to handle. Here's something most people don't think about when they compare cooling systems. Water isn't just convenient for carrying heat away from an engine. It's dramatically better at the job than air. Liquid coolant can absorb enormous amounts of thermal energy. It flows through passages cast directly into the hottest parts of the engine. It pulls heat away from combustion chambers and valve seats and piston crowns. Then it carries that energy to a radiator where it transfers into the atmosphere. The system maintains relatively even temperatures throughout the block. Hot spots get cooled. The entire engine operates in a controlled thermal environment. Air cooling can't do any of that. When you cool an engine with air, you're limited to removing heat from external surfaces. Everything happening inside the block, all that violent combustion, all that friction, all that mechanical stress, has to conduct its way outward through metal before the cooling fins can do anything useful. The surfaces closest to combustion run significantly hotter than areas farther away. Temperature gradients develop. Different parts of the engine expand at different rates. For the F6L912, this created stresses that accumulated over time. The area where each cylinder met its head was particularly vulnerable. In theory, careful shimming kept all the clearances correct. In practice, constant heating and cooling cycles caused expansion and contraction that slowly threw those clearances off. Run the engine long enough under heavy load, and components that fit perfectly when new would start to bind or crack. The pistons took punishment that water-cooled engines simply avoided. Without liquid coolant circulating nearby, they ran hotter by design. That extra heat accelerated wear, increased the risk of cracking, and shortened the interval between rebuilds. Operators who expected their air-cooled Deutz to last forever discovered that forever had a limit. None of this mattered much when power demands were modest. The original air-cooled designs from the 40s and 50s operated with significant thermal headroom. They produced relatively low power per liter of displacement, leaving room in the system to absorb heat spikes without distress. But customers always want more. Over the decades, expectations climbed. Tractors got bigger, implements got heavier, construction equipment took on larger jobs. The F6L912 was asked to work harder than its predecessors, producing more power from the same basic architecture. The heat load grew faster than the cooling system's ability to handle it. Operators started noticing patterns. On hot days, especially during harvest when every hour counted, engines would begin running warm. Warning lights would flicker. Temperatures would climb toward the red zone. The choice was either back off the throttle and lose productivity, or push through and risk real damage. Neither option was acceptable, but those were the only options available. Construction sites added another variable: dust. The same cooling fins that dissipated heat so efficiently also collected debris with remarkable enthusiasm. Fine particles stuck to oily surfaces. Grit accumulated in the gaps between fins. What started as efficient heat transfer became increasingly compromised as dirt built up. Keeping an F6L912 running properly required cleaning rituals that nobody had mentioned in the sales pitch: power washing before each season, compressed air to blast debris from between the fins, degreaser to cut through the oil film that turned dust into cement. Operators who neglected this maintenance learned hard lessons about what happened when airflow dropped. The fan belts demanded their own attention. These weren't accessories. They were the heart of the cooling system. If a belt stretched or cracked or snapped, the engine could overheat within minutes. There was no warning light that would save you. No backup system to buy time. Experienced operators stopped waiting for belts to show wear. Fresh ones went on at the start of every season as insurance against a failure that could cook the engine before anyone noticed. The irony was sharp. Operators had bought these engines specifically because they were supposed to be simpler than water-cooled alternatives. No coolant to check, no radiator to maintain, fewer things to go wrong. But the maintenance that air cooling actually required sometimes exceeded what a well-designed water-cooled system would have needed. The simplicity was real, but it came with hidden costs that only revealed themselves over time. And time was about to run out for reasons nobody in the 1960s could have predicted. For decades, the F6L912 existed in a world that didn't much care what came out of an exhaust pipe. Diesel smoke was just part of the landscape. Farmers and construction workers accepted it. Regulators, when they thought about emissions at all, focused on automobiles and left industrial equipment alone. That world started disappearing in the 1990s. Environmental regulations had been tightening gradually for years, but the targets kept getting more aggressive. By the 2000s, Europe and North America were implementing standards that would have seemed impossible a generation earlier. Two pollutants drove the entire conversation: particulate matter, the visible soot and smoke that diesel engines produce, and nitrogen oxides, the invisible gases that create smog and damage respiratory systems. Controlling these emissions required technologies that simply didn't exist when the F6L912 was designed. Nitrogen oxides form when combustion temperatures climb too high. The nitrogen that makes up most of our atmosphere combines with oxygen under extreme heat, creating compounds that regulations increasingly prohibited. Water-cooled engines could address this through precise thermal management, keeping combustion in a zone that produced power without excessive chemical reactions. Air-cooled engines had no such control. The F6L912 ran hot because that's how it worked. The high compression ratio that gave it such good fuel efficiency also created combustion temperatures that generated exactly the pollutants regulators wanted eliminated. Asking the engine to run cooler meant asking it to produce less power, which defeated the purpose of owning one. Particulate matter required different solutions. Modern emission standards demanded diesel particulate filters, devices that trapped soot in the exhaust stream and periodically burned it off through controlled high-temperature cycles. These systems needed precise thermal management to function. Too cool and the regeneration process failed. Too hot and the filter itself could be damaged. Integrating this technology into a water-cooled engine was complicated but achievable. Coolant temperatures provided stable reference points. Exhaust conditions could be managed through electronic fuel injection and sophisticated engine controls. The systems added cost and complexity, but they worked. For the F6L912, integration was nearly impossible. The engine had no electronic controls to speak of. Its mechanical fuel injection system couldn't provide the precise timing that after-treatment demanded. The space around the engine, already crowded with cooling fins and fan housings, left no room for bulky exhaust treatment components. And the fundamental thermal instability of air cooling meant exhaust temperatures varied too widely for the systems to function reliably. Europe's Stage 5 standards, fully implemented by 2019, set limits that mechanical fuel injection simply could not meet. The particulate target dropped to 0.02 grams per kilowatt hour, essentially requiring invisible exhaust. Nitrogen oxides had to stay below 0.4 grams per kilowatt hour, a threshold that demanded exhaust treatment systems the F6L912 couldn't accommodate. Deutz had seen this coming for years. Their technical bulletins began noting, diplomatically, that certain air-cooled models were best suited for markets without emissions regulations. That means that these engines couldn't be legally sold for new equipment in developed countries. The company had already invested heavily in water-cooled designs that could meet the new standards. The air-cooled line that had built their reputation was becoming a product for markets that most manufacturers no longer prioritized. By 2020, the transition was complete. Production of the F6L912 ended for any market with strict emissions requirements. Deutz committed to keeping spare parts available for engines already in service. But new manufacturing had stopped. An engine family that traced its lineage back to wartime innovation had finally reached a wall it couldn't climb. Standing back from the regulatory battle, a larger truth becomes visible. The emission standards accelerated the end, but they didn't cause it. The F6L912 was already fighting physics, and physics was winning. Every generation of diesel engines produces more power per liter than the generation before. Turbocharging, improved injection systems, better combustion chamber designs, advanced materials, all of these technologies have transformed what's possible. Engines today routinely produce twice the specific output that was achievable in the 1960s. But all that extra power generates extra heat. Air cooling couldn't scale to match. The basic architecture of the F6L912 was established when expectations were different. The cooling system had adequate capacity for the thermal loads of its era. As power demands climbed decade after decade, that capacity margin shrank. What was once comfortable headroom became barely adequate, then insufficient for the hardest working conditions. Deutz could have redesigned the cooling system. Larger fins, more powerful fans, better airflow management. But each improvement added weight and complexity while delivering diminishing returns. At some point, the engineering required to make air cooling work at modern power levels exceeded what the technology could reasonably deliver. Water cooling simply made more sense. The company's response was to develop entirely new engine families. The TCD series that replaced the air-cooled line used liquid cooling, turbocharging, electronic fuel injection, and integrated emissions controls. These engines met Stage 5 standards while producing significantly more power than the old designs ever managed. They ran quieter, smoother, and more efficiently. They were also fundamentally different machines. The TCD engines required coolant maintenance that the F6L912 never needed. They contained electronic systems that demanded diagnostic equipment. Software updates became part of ownership. Repairs that an operator might have handled with basic tools now required dealer involvement. The independence that air-cooled Deutz owners had prized was gone, replaced by capability that came with new dependencies. Whether this trade-off was worthwhile depends entirely on what you value. If you need maximum power, minimum emissions, and optimal fuel efficiency, modern engines win without question. If you value the ability to understand and repair your own equipment, to keep a machine running in remote locations without specialized support, the calculation looks different. The production lines may have stopped, but F6L912 engines haven't disappeared. In regions where emissions regulations don't reach or aren't enforced, these engines continue working exactly as they always have. Developing nations remote agricultural operations, industrial applications in places that regulators have never visited. The old air-cooled Deutz units keep showing up wherever reliability matters, more than compliance. The aftermarket has proven surprisingly durable. Parts suppliers continue stocking components for engines that left factories decades ago. Rebuild specialists have developed expertise in returning worn units to like-new condition. The modular design that made field repairs possible in the 70s still makes comprehensive overhauls practical today. A competent mechanic can bring a tired F6L912 back to full health using techniques and tools that haven't changed in half a century. Collectors have discovered these engines too. The distinctive sound of 6 cylinders breathing through cooling fins has become sought after by people who appreciate mechanical authenticity. Restored equipment featuring F6L912 power goes for premium prices at shows and auctions. What started as purely utilitarian machinery has taken on nostalgic value that its designers never imagined. More significantly, the engine's philosophy continues influencing how designers think about durability and serviceability. The modular approach to engine architecture means that operators can repair rather than require factory technicians, shaping expectations across the industry. Every modern engine designed with field service in mind carries some trace of the thinking that Deutz pioneered. The story of the F6L912 is ultimately a story about trade-offs. Every engineering decision creates advantages and disadvantages. Air cooling eliminated certain failure modes while creating others. Simplicity reduced some maintenance needs while demanding different kinds of attention. Robust construction extended service life until external requirements made the whole approach obsolete. No design lasts forever. The world changes, and the regulations tighten. Technologies that dominated one era become inadequate for the next. The F6L912 dominated its era because it solved problems that mattered in that specific moment of history. When the problems changed, the engine couldn't adapt. Modern designers have internalized this lesson. Today's heavy-duty diesels use liquid cooling not just because it dissipates heat more effectively, but because it provides the thermal stability that emission systems require. Electronic management has replaced mechanical simplicity because regulations demand precision that cams and springs cannot deliver. The engines are more complex, harder to service without specialized equipment, dependent on software that users cannot modify, but they're cleaner, more powerful, and more efficient than anything from the air-cooled era. The F6L912 existed in a moment when the balance still favored simplicity. That moment passed, but the engine's influence hasn't. Every time a designer considers how equipment will be serviced in difficult conditions, every time a manufacturer builds modularity into a machine for easier repairs, they're working within a tradition that engines like this one helped establish. So what do you think? When we retire a technology that worked for 50 years, are we always moving forward? Or do we sometimes lose something worth keeping? Was the F6L912 a relic that needed to go, or proof that older isn't always worse? Drop your thoughts in the comments, and if you enjoyed this one, subscribe for more stories about the machines that built our world.